Hi guys, Assalamu alaikum. This is Arif. In this video, I am going to show you how we can design a ROM first in VHDL and then in a Verilog project. So ROM is actually a component where we store our program or from where we can give the input to our program like a CPU or anything like that. So this is a VHDL program first. Here first I have defined some libraries which I am going to use in my program, and after that I have defined an entity which has name program ROM, and it has two ports. One is input port PC, which we are going to use as an index to take out the values of our program, which are going to be hex values. And then there is another port which is going to be output port, which is going to give us those values like those hex values. And this is like 16 bits, and these address bits range are like 8 bits. And after that I have defined this architecture of my program, and here I am going to first define a type, and my type is ROM type, and it is actually my ROM, which is like a array. So its width is like 16 bits and its depth is 11. So after that I am going to define a signal, and that signal is variable, and that is of this type ROM type which I have defined here. And here I can give my input, which are going to be the x values, which can be our input to any program. So this is a hex value, this is a hex value also. This is the way we can give the input to our ROM. And after that there is begin block, and in the begin block there is one code line. So actually this is the index which is going to take out our values from our ROM location, and that value we are going to place into our code, and this code is going to be our output. So let's go to our test bench first and see how the test bench is defined. So in the test bench, after defining the libraries and the entity test bench, I am going to define my architecture, and in this architecture I am going to use that component program ROM, which we have to do in any test bench. And after that I am going to define two signals, PC and code, which we are going to connect to our component. And here after the begin block starting, we are going to use these signals, and this is the same component which we have defined in our main program ROM. And this is the way we are going to call this in the begin block. And after that in the process block we can give our stimulus, and we can say first of all PC's value is going to be 00 index, and give us the value at that index. And then after waiting for 10 nanoseconds we are going to say start a for loop, and in that we are going to increase the PC value one by one. And then we can end this loop as well, and after that we can check whatever is stored at the last value of our PC, at the last index of our PC. And then we are going to wait for 10 nanoseconds as well. And here in the process block we have to use a wait statement as well, so that the loop doesn't run for the infinite time. And then end process block, and after that we are going to finish our architecture block as well. So I have compiled this code already, so let's try to run this program and see how this program is behaving. So we can right click here, simulate, and we can check our wave here as well. Select both ports, input and output, start simulation. We can expand it, zoom in. So we can see our PC is going to increase by 1 and it is going to give us these 8 values. It is going to pick up those values from the ROM and give those as outputs to this code. So I can show you where the code is. So these values, this is at index 0, PC0 value, this is PC1, PC2, and same way they are going to PC8. Let's end the simulation. Instead of using these two functions, unsigned and toInteger, we can get the value. For these two functions, we have to use this library as well. This library, numeric underscore std.all. And instead of using those two functions, we can use actually a third function as well, which is placed in another library, for which we are going to use this code line. So convert integer is going to be that function which we can use to get those values as well, and this function is from this library actually, unsigned.all. So let's try to build and run this program again. Compile this program. There is no error in compilation. And let me show you one more thing. Instead of giving these values in this program directly to our signal where we have defined, we can do this as well. There is another way that we can define our signal separately outside this begin block like the way we did previously, but we can give our values like this by using the index locations. We can store the values inside our ROM. This is just another way of storing the values first and then getting those out through this code line. So let's compile this, save and compile this program, and then we are going to check this program as well by doing the simulation again. Compile, and let's go to Testbench as well. So in the Testbench, this library unsigned.all we are going to use for this plus sign, and this time I am going to increase the PC by 2. So just a little change in the Testbench as well. Compile selected. Now let's start the simulation. Run the simulation and let's see the values. So this time we are increasing PC by 2, 0 to 4, and 4 location is going to give us this code, 6 location, this one, 0 location, this FF. So this is pretty much the complete program of our ROM in the VHDL language. And now I am going to flip over to the Verilog project, and I am going to show how we can do the same design in system Verilog. So now I am in my system Verilog project, and I am going to show you that program is this one. You can see here we have defined program ROM as module instead of entity inside system Verilog, and after that we have defined two ports, which is going to be like input port, PC output port code, just like Verilog. And after that we are going to define this ROM as reg. This is ROM variable. This ROM, its width is from 0 to 15 bits width, and then its depth is 0 to 255. So in Verilog actually we can define our ROM with a great depth as well, although we are going to give just 11 or 12 values to that, but in the case of VHDL we have to define just that width for which we can give the values, otherwise it is going to give us the error. So it is fine in Verilog. So these are just little differences in this initial block. First we are going to use these values. I am going to show you how we can define. There are two ways we can give the input to our ROM or store values inside our ROM. So in that ROM variable, to these indexes and this equal sign inside this initial block, we can give the inputs like this, those x values, and after that we are going to assign those whatever our values are stored at a specific location. We are going to use the PC as an index, and we are going to collect those values from our ROM through this PC index, and we are going to give those as output to our code. This is our code output code variable. Save this program, compile this, and I am going to show you actually it's Testbench as well. This is the Testbench where we are just calling that function again, that program ROM module like this. And here we have also given as reg, which is our input. We give it as reg code. Our output, we are going to define it as wire. This is the way we do it in Testbench. After that initial block, and in the initial block we are going to start from PC's value is equal to 0, and after that we are going to give it a delay of 10 nanoseconds, and after that we are going to increase that PC value. Let's do it this time by 2. We are going to increase PC value by 2, and after that we are going to check whatever is stored at PC value, the highest value of PC. So this is our program. Let's simulate this program as well. So we are going to go to this test bench and simulate this. Drag these two ports inside this window. Let's run the simulation and let's see. So we can see our output PC index 0 value is 0, at index 2 value is 2, and index 4, just like in our program we have given value is 444, and same way 0A value is FFF. Let's close this simulation. And in Verilog also there is another way through which we can give the, or we can store the hex values inside our ROM. So this time instead of using this initial block to give to store the values inside my ROM, I'm going to not use reg to define my ROM. I am going to define my ROM as wire, and once we are going to define that ROM array as wire, we can assign the values to it like this. So these are the same values, same index where we are going to store these x values through this assign. fire and assign, reg and no assign. We are going to use reg inside initial block to give our program the values. Rest of the program is going to stay same. Let's compile and run this program. These are just two different ways to design our ROM inside VHDL and Verilog. Compile this program. Let's try to change the test bench as well. This time I am going to increase the PC by 1. Let's simulate this program again and let's check the output. So we can see at 00 index this value is stored, at 05 PC index this value is stored, X value at 08 this value is stored. So this is the way we can design a ROM inside system, Verilog and VHDL. So thank you guys. I hope you guys have enjoyed this video. Have fun.